Hi, it is my pleasure to introduce STeLLAR, an open source framework that clears the serverless clouds, shedding the light on their performance. What keeps the cloud users awake at night? Actually, just two thoughts. First is how to manage the cloud infrastructure that their services use and avoid any trouble. Second is whether their services are fast enough to keep their clients happy. Good news, the new programming paradigm called serverless frees cloud users from the first major headache. Serverless clouds allow cloud users to focus on writing their code as a composition of functions, whereas the cloud providers take care of functions deployment and automatic scaling of function instances according to traffic changes. This labor division boosts developers' productivity, allowing fast time to market for their products. Okay, so cloud providers have eliminated the first major headache, and this talk seeks to eliminate the second haunting thought. Serverless clouds keep their secrets because their infrastructure tends to be proprietary. What performance should the cloud users expect from their applications? Our key observation is that serverless clouds feature the following fundamental components, namely, the cluster scheduler that is on the way of all incoming invocations, selecting or spawning the appropriate instance for each invocation. The fleet of the worker nodes where function instances can run, and the storage service that holds the initialization state of functions. For example, function container images that are used for spawning new instances of these functions. The same storage is used for transferring data across functions. With this insight, we introduce STeLLAR, an open source framework for performance analysis of serverless clouds. By configuring function characteristics and the load scenarios, STeLLAR can stress and evaluate the performance of each of the three fundamental components separately. We showcase STeLLAR effectiveness by comparing three leading cloud providers, namely AWS Lambda, Azure Functions, and Google Cloud Functions, comparing their performance against one another. First, we evaluate the response time of warm and cold invocations by steering invocations to these functions once at a time with a different interarrival time. Invoking functions frequently, for example once per second, results in warm starts, whereas invoking them once in 30 minutes causes cold starts, where a function instance needs to be spawned before an invocation can be processed. The charts show latency CDFs on the y-axis and latency in milliseconds on the x-axis, with warm invocations on the left and cold invocations on the right. Note that x-axis limits on the two charts are different because cold invocations are much slower than the warm ones. One can see that warm invocations are much faster than their cold counterparts. However, in both cases, latency variability that we measure as 99th percentile divided by the median latency, also referred to as tail to median ratio, is quite moderate. Next, we study the communication delays for the application of two functions, where one function transmits a payload of a configurable size to the second function. Since functions are stateless, data is transmitted via a storage service where the first function saves the payload to the storage, and the second function loads the payload from the same storage. We capture these latencies with timestamps taken by the user code in these functions. On the left chart, one can see that the median latencies are shown with solid lines, and tail latencies are shown with dashed lines. On the right chart, the CDF lines are for 1 megabyte and 1 gigabyte payload transfers, respectively. Clearly, storage transfers are slow and have very unpredictable execution time. For example, for a 1 megabyte transfer in Google, these delays result in just 150 milliseconds median latency, but entire 6 seconds in the tail latency, yielding a tail to median ratio of almost 40. We studied the response time of functions in the presence of bursty traffic with long execution times of functions of 1 second to evaluate the queuing effects across concurrent invocations of the same function. We find the choice of the scheduling policy dramatically important for function and response time. In this chart, solid lines represent CDFs obtained by sending individual invocations, and the dashed lines plot the CDFs for the invocations that come in bursts of 100. From the chart, it becomes clear that all three providers that we studied have different policies. AWS has little sensitivity to the burst size, meaning that AWS policy demands spawning a new instance on every invocation in a batch of concurrently arriving invocations. In contrast, Google and Azure show a significant increase in the median and tail latency for the bursty traffic compared to serving individual invocations. This means that the scheduling policy has a huge impact on the overall response time and cannot be ignored. Reasoning about performance of applications running in serverless clouds is difficult because the cloud infrastructure is obscure to cloud users. Our work introduces STeLLAR, an open source serverless benchmarking framework that enables performance and even tail latency analysis of serverless clouds without an access to their proprietary components. Our analysis identifies that modern serverless clouds have the same fundamentally required components, namely the scheduler, the storage service, and the worker node fleet. Out of three, storage and scheduler are the key performance bottlenecks across the three leading providers that we studied. These are just the highlights. Please see more of our studies in the paper. STeLLAR clears the serverless clouds. Now check our framework online and join the community on GitHub. Thank you.